There are 20 people here, so I can wait for another half a minute.
That's good.
Marco is here.
No, he had to leave. So yeah.
No, I mean Marco Campi.
Marco Campi, yeah,
yes,
he's here.
It's
I
really
can see him
important.
twice.
Present.
Okay, so is it? Okay, so let's start. So today's invited speaker is Marco Campi. So he is a professor of automatic control at the University of Brescia. So his field is automatic control, and machine learning is just one of his interests. He's done some excellent work in this field. He invented a guaranteed error machine, for example, so it's in his 2010 paper in machine learning. Also interval predictor models. So these are methods that have guaranteed validity, some validity guarantees. So it's very much like informal prediction, but it's conditional. Usually he's interested in methods where validity is conditional on the training set. So in conformal prediction, it's unconditional. And of course, we try to achieve some conditionality, different versions of conditionality, like on the training set, on the test object, or on the test label. But here it's mainly on the training set. So it would be great to establish some connections. So he's very well known in his field of automatic control. So he's a fellow of the Institute of Electrical and Electronics Engineers. So he was elected for his work, for his contribution to stochastic and randomized methods in systems and control. He's a recipient of the Georgia Quasar Prize, XLB Outstanding Paper Award, and he's given many plenary addresses at major conferences. Okay, so it's great to have him here, and his talk is Risk and Complexity in Prediction Problems. So over to you, Mark. You're muted, Mark.
Yeah, he has a recorded presentation, so we'll start it now.
Sorry.
Yeah.
Sorry.
So it's great being at COPA this afternoon, and I take pleasure in delivering this plenary address about a research topic of mine that I have been developing over the past probably 15 years, and it has strong relations to the concept of a conformal prediction, as we shall see. Let me say, first of all, that my first encounter with the conformal prediction was some 10 years ago. At the time, I was studying classification problems and was developing a methodology called GEM, Guaranteed Error Machine, and I came across a conformal prediction, and I also had a correspondence with Professor Wolf. And I told myself, hey, that's great stuff. I have to learn more. And also, since that time, I cherished the idea of meeting in person with Professor Wolf and other people in the same business, like Professor Gammerman and Professor Schaffer. That time, you know, at times gets complicated. So time went on, and 10 years had passed. And when I was invited to give that presentation here at COP, I told myself, that's eventually as the opportunity to meet with these people. And then, you know, the pandemic hit. And so I'm still here in front of my computer recording this presentation. So that's a pity, but I do hope that there will be an extra chance for meeting in person in the near future. And with occasion, I also would like to thank the organizers for inviting me to give this presentation. It's a great pleasure, and it's indeed an honor. Before anything else, before I start, I would like to tell you immediately the take-home message that I will try to convey to you in this presentation. So you see my slide here, and the title is Risk and Complexity in Prediction Problems, and the two keywords are risk and complexity. So risk in short terms is the probability with which something goes wrong in prediction. You make a statement, you say, okay, I predict that this is going to happen, and instead it does not happen. And the probability for that to happen is the risk. Complexity instead refers to the complexity of representation of the solution, and it has to do with compression schemes. Complexity in science is quite a tough word to deal with, and the eminent people like Kolmogorov himself has worked with this concept. Here the concept is more specific, is complexity of representation. And the take-home message is the risk can be evaluated starting from the complexity. The risk is a quantity that depends on the underlying mechanism by which observations are generated, and therefore it cannot be directly computed. So, for example, you have a population in front of you and you have different members of that population coming to you, and the risk depends on the probability with which different members are seen. In contrast, the complexity is a measurable quantity. So I give you a set of data points, you can compute the solution, and on top of that, you can also compute its complexity. In other words, the complexity is a statistics of the data, is an observable. And therefore, it's very important that the risk and complexity are linked to each other at a very general level, because from an observable quantity, the complexity, we can judge the risk, which is the unknown, and it's the quantity that we want to know when we run an application. Before anything else, I would like to thank these three guys because this presentation wouldn't be possible if it was not for the presence of these three people. Particularly, Simone Garatti on the left was a student of mine till 2004. Then he moved to the Politecnico Milano. He's a faculty there now. And with Simone, we work on a weekly basis. Simone is an absolutely brilliant person. He is so deep. He doesn't speak too much, but when he says something, you better listen to him. And by and large, my presentation today is based on my joint research with him. Then we had other two people here. Algo in the middle was another student of mine till some 10 years ago. Then he became sort of a globetrotter in Australia for 2 years, and then 1 year in CWI Holland, and then stuck in Budapest. Algo is another very, very deep person, and he has such a broad knowledge. So it's a great pleasure also working with Algo, and we're doing a lot of research in the same field together. And the same for Federico, another brilliant person, and he knows a lot of maths. So should you have any problem in maths, just knock at his door and he has the answer for you. He knows way more maths than I do. With Algo and Federico, we are developing a lot of results in connection with the same topic developed here. And so all the three guys here are very important to me, and I really enjoy working with him. And my deep appreciations goes to these three researchers. Okay, so let me get started now. When I deliver a presentation, very often I prefer to go bottom up, from particular to general, because I believe that concepts can be convey to a large audience better starting from significant examples. And then later we are going to see the theory. So in this first example, we have 500 points drawn from a common distribution and independent of each other. So it's pretty much like having a handful of blue spots and or blue dots, and you throw them on the screen. Next, we want to construct a predictor for where the next point will be. And my construction is the following. There is no claim of being in any sense the best possible construction, but I do the following. I construct the convex hull of the 500 points, which in areas the smallest convex set containing all the points. And then my claim is the next point will belong to the convex hull, which means that if the point is inside, like the green cross here, is then right. If the point is outside, I'm wrong. And in this case, let me use my pen here, the probabilistic mass which is outside the convex hull is the risk. Now, you take a look at this picture for this particular construction and you start arguing the following way. I do have 7 points at the boundary. So one is here, another one is there, another one is here, 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 and here. Whereas all the points are inside. So you may develop the idea that the risk could be small, because after all, almost, the vast majority of the points are inside your convex hull. So kind of learning from past experience, you may expect that the next point will also be inside. So 7 points at the boundary in this case, and intuitively the risk should be small. I have a second example for you, just contrasting what we had before to better explain the concept. Again, I drew 500 points for you, but this time from a different probability distribution. And it so happened that 492 points were at the boundary. Now, if you ask me which situation do you prefer, then if I'd value keeping low the risk, I would certainly say the one on the left. And I believe that you all would say the same. So the intuitive idea underlying this choice is that having many points inside implies that the risk is low. Okay, so this first example leads us to the concept of complexity that I would like to introduce by still referring to the same example. So what we saw before is we've got 500 points, P1 through P500, and we feed an optimization algorithm. And by the way, the optimization algorithm was this one, where we minimize the volume of our set, wrapping up the points, and we choose S from the set of all convex sets on R2, subject to the constraints that each and every point, P1, P2, P3, and so on, are in S. So it may look like a innocuous looking problem, but you may also notice that it belongs to a fairly complex class of problems, because to start with, it is not a finite dimensional optimization program. Reason is that the set of convex sets does not have the structure of a finite dimensional vector space. No matter what, repeating what I told you before, in the first example we had 7 points at the boundary. So this means that I can remove 1 point which is inside my convex hull, another one, I can keep going until I'm left with the 7 points at the boundary. And the very point is, if I now run the same optimization program over just those 7 points, then the program returns the same solution as before, as when I had all the points in place. And this leads me to this concept of complexity of representation. So the complexity of representation is the size of the smallest set, such that if I take that set of points and I feed my algorithm with just those points, then the algorithm returns the same solution. So it's indeed a concept of complexity of representation in terms of the whole set of data points I have. And intuitively, low complexity implies low risk, and let me just repeat, that's a general concept with the applications to various fields, machine learning, but also quantitative finance, robust control, etc. So one thing that I would like to mention is that in this presentation, I will be referring to risk as the probability of misprediction. However, the concept of risk carries over to more general setups than that. For example, here I mentioned robust control, and actually my original background was in control. And there, for example, you might say, I have an uncertain plant, and I would like to design a stabilizing controller for the plant. And it may happen that the controller you have designed does not stabilize a given instance of the uncertain plant. And the probability for that to happen is again a risk. So I'm just mentioning the fact that the concept of risk is more general than the probability of misprediction. Is more generally the probability that something goes wrong, which is having different interpretation depending on the application at hand. But by and large, in this presentation, risk for me is just referring to prediction. So this first example serves the purpose of introducing the concept of complexity of representation. But I do have another example for you, which matters to me because it is introducing the connection between risk and complexity. So again, this is coming from a optimization program, and I'm going to describe for you by using my hands. In this case, we have points taken from a 400-dimensional Euclidean space. And we do have 1,000 points. So I have this cloud of 1,000 points. And what I do is that I'm going to explain in 3 dimensions. I consider the negative orthant, which is as follows. So this is the region. And I take negative x, negative y, negative z. So that's negative orthant. I have my points. I lift and then I go down as much as I can in all directions so that all points are kept inside the orthant. So it's similar to the conversal, but in this case, I construct an orthant. And now, the complexity in this case is given by the number of points that are at the boundary. So in 3 dimensions, it may happen that you've got 3 points, one here, one there, or can be just one, for example, in the vertex. So in other words, depending on the sample data points we have, you can experience 3 or 2 or 1, and in 400 dimensions, everything can happen from 1 to 400. So in other words, it is the complexity is a random variable, depends on the sample we have C. Now, given the solution, I can also compute the risk, which is the outside probabilistic mass. just let me remark that in a real application, I cannot compute the risk because I do not know the probability distribution. All I have are the data. But here I can, because I manufactured the example, I manufactured the distribution, so I can compute both complexity and the risk. Now, given 1,000 data points, you find the solution, you compute the complexity and the risk, and you have a point in a two-dimensional domain, risk and complexity. What I did for you here was that I kept drawing 1,000 points, then another 1,000 points, then another 1,000 points. I computed the corresponding solution and then risk complexity. And by Monte Carlo simulation, I constructed the bivariate distribution that you see on display right now in my slides. So the complexity is here. It is an integer quantity ranging from 1 to 400 because this is a convex optimization program, and then as a result of Helly's lemma, you never experience more than 400. The risk is a continuum quantity ranging from 0 and 1. And this is the bivariate distribution. Now, if you take a look at this distribution, you immediately observe that there is quite a bit of correlation between risk and complexity. This means that if in a run I compute the complexity and it turns out to be 250, I say, hey, but then I'm here, and hence the risk is between here and there. So I can judge quite tightly the value of the risk. Just notice the following. If you marginalize, so you take, you project to the left and you take the marginal distribution of the risk, which I'm going to highlight here for you, it is this one, then this is quite spread. It goes all the way from 0 to 0.4, hence, a priori, if I were asked how large the risk is going to be here, I would say, okay, I expect between 0 and 0.4. But then if you wait and you compute the solution and then also the complexity, based on this extra piece of information, you can tightly judge the risk, which is not to say that the risk is one value. It still has stochastic fluctuation, but that's minor. So you can tightly judge the risk. And I repeat this point because that's important. The complexity is a measurable quantity. You can measure from the data sample you have, whereas the risk is not measurable in a real application. Now, having observed that, of course, you can ask very important questions here, and the most important of which is, but this strong correlation between risk and complexity is a consequence of specificities coming up in this example, or is more general than that? Now, the truly surprising fact is that this result holds true universally. In other words, risk and complexity are linked to each other in a very general setup and totally distribution free. And this leads us to the following slides where we're going to see some theoretical results. So to start with, the setup that I'm considering here is the following optimization program where we minimize a cost function subject to constraints, and each constraint is associated with an observation delta I. So I have observations delta 1 till delta n. Each sets a constraint, and small x must be in a set as given by delta I. Now, this framework is fairly general. So this variable belongs to any possible set. So it can be that is x in a finite dimensional Euclidean space or infinite dimensional vector space, or even beyond that. The theory applies for x belonging to any set, even without any algebraic structure. Again, the set here is totally general, and delta I comes from, the delta i's come from a common distribution. They are independent of each other, and the distribution is totally generic. So it's a totally distribution-free theory. I don't have much time to discuss the generality of this setup. Just one additional remark. Someone might say, well, this cost function is deterministic, but my cost function depends on delta. Well, just let me remark that should C depend on delta, you could always go back to this formulation by an epigraphic reformulation. Okay, so let's take this very general setup, and then the following theorem holds. This was proven in year 2016 in mathematical programming. As a matter of fact, the underlying theory has been developed over 4, 5, 6 years. So this story was initiated some 10 years ago. Now, the theorem says the risk is upper bounded by a function epsilon that depends on the complexity with a very high probability. So the probability that the risk is bounded this way is at least 1 minus beta, and think of beta as a small number, a very small number, something like 10 to the minus 6. And this beta is given by this variational problem on polynomials of degree n. I'm not trying to describe all the mathematical aspects here in an oral presentation. So for details, go to this paper. What I value is to get the interpretation of the result through. So let me interpret the result for you. And for that purpose, let me go back first to this example. So I first tell you what the theorem says in this particular case. So if you take an initial view, is it from the top, then you can draw a line like this, and you have barely any probabilistic mass above this line, which means that the risk can be upper bounded based on the complexity with the very high probability. Now, this result holds true universal. And this theorem is depicted here in this picture for when n is equal to 1000 data points, and beta is minus 6. Here you have complexity, here you have risk, and you have this curve. And the theorem says the probability of being here is no more than to the minus 6 universally for all problems. All problems in the universe are such that it's totally distribution free, are such that the probability of being in the pink region is no more than 10 to the minus 6. Now, how do we use these results? If the complexity is 100, you compute this value and you claim the corresponding risk, 150, 50, and so on and so forth. Okay, so this result holds true universally and links or upper bounds the risk based on the complexity. Next, I would like to contend that this evaluation is pretty tight. And in order to explain this point, let me first refer to a subclass of problems. And I consider here the subclass where there is only one irreducible support set. Let me explain this. So a irreducible set, support set, is a set of data points such that if you feed your algorithm, you get the initial solution. And it is irreducible if you cannot remove any point from it without changing the solution. So that's irreducible. It may happen that there are two irreducible support sets, and that this assumption is requiring that there is only one. And of course, the size of this irreducible support set is the complexity. For example, this assumption rules out the possibility of concentrated mass over observations. Importantly, we have a second assumption, and it is that the complexity is always the same. This is a number. Let's say D is 100. So in other words, the complexity in this subclass of problems is not a random variable. It's something that you know in advance because it's always the same. Is a fixed deterministic number. And you may wonder what kind of problems I have in mind when I refer to this. So in this paper, 2008, we called these problems fully supported. And here it is an example of a fully supported problem. That's the construction of a Chebyshev layer. Let me describe this. We've got here points in R2. These are data coming from a distribution, and they are IID, independent and identically distributed. Now, you try to construct the smallest layer that contains all the points, and the layer is centered around a polynomial. And you play with the coefficients of the polynomial. So you shape up the polynomial so that you minimize the maximum distance of the vertical position of data from the polynomial. So you squeeze your data points within the Chebyshev layer as much as you can by shaping out the central line to a proper selection of the theta values. Now, claim whenever the probability from which data are drawn has a density, whenever it has a density, this problem is fully supported, so it satisfies these two conditions. I come back to this. However, the point is that for this subclass of problems, we do know in advance the distribution of the risk, because the distribution is always the same. Is a universal distribution for all problems belonging to this class. This is a beta distribution, and for example, for n equal to 1000, d equal to 200, the density of the beta distribution is this one. Let me make a connections with the conformal prediction. You may want to say that those D that are forming the support sets are those points that are less confirmed. And if you take the expected value of the beta distribution, you find that this value is D divided by m plus 1, which is exactly the result that we have for the expectation of the risk in conformal schemes. As a matter of fact, there is a structure which is the same as for conformal prediction in this context, but we know more than that. So in this context, we do know the whole distribution of the risk. this distribution is invariant. And based on that, for example, I can say, okay, this point here, such that the tail has a probability 10 to the minus 6, so I may claim that the risk is below this value with the high confidence 1 minus 10 to the minus 6. When I first established these results came to our surprise, because let me go back to the Chebyshev example and let me read what the result says in this context, which is kind of surprising. It says, well, in this case, the risk is the probabilistic mass which is outside the Chebyshev layer. And the result says, no matter what the initial distribution from which data are drawn, it can be Gaussian, it can be bimodal or whatever, then the risk has always the same distribution, always. Of course, the shape of the layer will depend on how your sample points distributes, but the risk is always the same, and hence we know the distribution of the risk, and we can use it to come up with the evaluations of the risk. And let me also mention that this carries over to even more general setups. For example, we can do trigonometric interpolation instead of polynomial. All right, so let me sum up, because you might have lost the thread here. So we are having two results. One holds true for the class of fully support problems, which is a subclass of problems. And for that class, we know in advance the distribution of the risk, and the complexity is fixed and deterministic in this setup. And we do have another result that holds true in full generality, where the risk is bounded based on the complexity. Now, the question is, how do these two results merge together onto a common picture? And they do the following way. So, if I take a problem belonging to the class of fully supported problems with E equal to 200, what I know is that the complexity is all the time 200. Sorry. Oops. So there is nothing here and nothing here. And on top of that, I know the distribution, which is this one, which is the beta distribution. Hence, I can compute this red dot. And since I know that this tail has probability 10 to the minus 6, I know that any theory which is valid in full generality may not claim anything better than the red dot. So I'm going to repeat this. This curve, this blue curve, holds true for all problems in the universe where complexity is a stochastic variable. Then I have a subclass of problems where complexity is fixed beforehand. And for that subclass, I can compute exactly the boundary where the risk above that boundary has probability 10 to the minus 6. And since the other result holds true for all problems, then the blue dot, this one, cannot be below the red dot. Of course, I can repeat the same exercise for fully supported problems in dimension 200 and 250, 300, 270, 150, and I can form my red dotted curve. And by the look of these two curves, the blue and the red, you see that they are quite close to each other, but they are not one on top of the other, they're different. And now the red curve is exact because it's known it's based on the known beta distribution, which is exact, whereas there is no claim that the blue cannot be improved. There's no claim that the blue is exact. And hence, you may want to ask the following fundamental question. Is the red curve a valid curve for the general problem where we do not know in advance the complexity of the solution? The complexity is a random variable. Well, the answer is no. The red curve is not feasible at that level of generality. I believe that this result has a very strong epistemological value, which I would like to express this way. Simple questions are more guaranteed than simple answers. So let me explain this. Say that I come to you and I say, I have a fully supported problem and D is at 50. So we know in advance that all the time the complexity is 50. Then you might say to me, well, then you're asking a simple question because the complexity, you know, at the time you ask the question, that it is small because 50 is a small number. That's true. And then you can claim the red. Say instead that I come to you and I ask a question which is not simple because the complexity may range over the whole span. And you a posteriori verify that the solution is having complexity 50. So the solution is simple, not the question. Then you can claim the blue. Hence, simple questions are more guaranteed than simple answers. However, from a quantity point of view, you see that these two curves are quite close to each other. So the difference in degree is minor. And I would say that this theory can be applied across many different fields when you do machine learning, prediction, but also quantitative finance, robust control, and more. And to all people using this theory in applied problems, I would say there is little to gain from a priori studying the problem. So that you study the problem trying to prove that a given problem is fully supported of some size. I mean, the payoff is minor. And the message is wait and judge from the complexity of the solution. And this also explains this title I got up there, wait and judge. So I give you data points, you can compute the solution, then also evaluate the complexity, and based on that, you can judge the complexity based on this curve. Okay, I have one more point that I'd like to make. So we have a general theory, complexity versus risk, and then we consider a subclass of problems that is fully supported. Now, let me concentrate on this, which was the first condition defining fully supported problems, but I drop the assumption that the complexity is deterministic. So the complexity is a totally generic random variable, but there is only one irreducible support set. I would like to let you know that in this context, there is an interesting result that says the risk is in sandwich between an upper function and a lower function that depends on the complexity. So let me again explain with the picture. The result says in dimension 1000, the probability of being above the one of the two curves or below the other is at most 10 to the minus 6. So in other words, the density has to stay in this region here, the density or the distribution. Let me explain or exemplify back with my second example, the one with the orthant in 400 dimensions. You saw this picture before. So as you can see, the distribution is within the lower and upper limits. I have run a second example for you where the distribution in 400 dimensions is different from what I had before. And you can see that the two-dimensional risk complexity distribution depends a lot on the initial distribution in this context. So for example, the marginal here is this one, and here is this one. But what matters is that the distribution is always between this upper and lower limit, and hence I can tightly judge the risk from the complexity. Okay, so time flies, and I would like to quickly go to a setup which is even more general than what I've been discussing so far, because that's important in particular for applications. So what we had before was exactly this type of optimization programs. Before I wrote this constraint as x in x delta I, now I'm using a function f. Of course, the two ways of writing the constraints are interchangeable. But I prefer in this context to use the f function because in a minute from now, this f will play the role of regret for violating a constraint. So this is the setup we had before. So someone might argue that this setup is a bit stiff. And the reason is that I'm rigidly enforcing all the constraints. So I see observations, let's say 1,000 of those, and I enforce that all the 1,000 constraints are being satisfied by my solution. This is a bit rigid. So people that are using data in various disciplines like system identification or signal processing know that accommodating all the constraints may lead to poor solutions. So this is what is called a robust solution with respect to the observations. And it's poor because there might be observations that are kind of weird as compared to others. So with the terminology that I don't particularly like, people speak of outliers. And the outliers are dictating the solution. And the solution becomes mainly given by some of the observations, the weird ones. Let alone the fact that if you are adamant in requiring the satisfaction of all the constraints, you may end up with a situation which is infeasible. So just to mention this, if you use a support vector machine and the points are not linearly separable, and you apply this, then the problem becomes infeasible. So the idea here is that, okay, I would like to go up to a more general setup where I relax my constraints. So instead of saying I want to have here 0, it's a variable ci, which is bigger than or equal to 0, and I allow my f to become bigger than 0, like ci, but I pay a penalty for that to happen is given by the sum of the xi's in my costs. And this rho, this coefficient here in front, is something that you can play with. So if rho is taken to be very large, basically you're back to the context where no constraint violation is allowed. By decreasing the value of rho, you trade constraint violation for a better solution. And let me just mention that in machine learning, all problems belonging to the class of support vector methods have the structure. So SVM is this one, or SVDD support vector data description is this one, SVR support vector regression is this one, and I'll come back particularly to SVR in a couple of minutes from now to give you a numerical example. But let me make a very important point here. I want to claim that the previous theory applies to this context. In this case, my concept of complexity becomes this one here that I read for you. So it is the size of the smallest set of observations of data, where first I have the data points corresponding to violated constraints. So Xi bigger than 0 means that I'm violating the constraint. Xi at optimum bigger than 0. And on top of that, I add more observations so that the whole lot of data points here allow me to reconstruct the solution X star, the optimal solution. You may wonder why I insist to call this complexity. And I already know that there is a bigger story than the one I'm delivering here. In this presentation, I'm referring to optimization, but all this story carries over to a more general setup of decision making. And in that context, the concept of complexity remains exactly the same as the one I've given for the standard optimization problem. However, when you go to that level and then you go back to this level of relaxed optimization, the concept of complexity there boils down to this notion of complexity. So in other words, there is a claim here that this is the correct notion of complexity as coming from a more general theory. And for those interested in this more general theory, you can refer to this a paper at the bottom of this slide. Now, the point is that if you adopt this concept of complexity, exactly the same results, same theorems as before apply. So, for example, you saw this before where risk is in sandwich between an upper limit and a lower limit. Now, let me make a digression here. So I do value results of this type where the number of data points n can be any. So this result holds true when the number of data points is 100, 50, or 1000. So it's a finite dimensional. It always applies. And just keep in mind that in a real application, we all the time have just finitely many data points. However, you still may ask what happens when we take asymptotics, when the number of data points tends to infinity in this theory. And as a corollary of this theorem, we have this result, that the risk tends to risk hat. And the risk hat is the ratio between complexity and the sample size. Let me pause a second and I would like to make a remark because I believe this is important. Probably this matters to many people in the audience, and I would like to make a connection with the Vapnik-Tregonenko theory at this stage here. I do know that Professor Vapnik is in the audience, so it's an honor for me to speak in front of him. And that's also why I want to make this, this connection. So in the late 60s, Vapnik and Chervonenkis established what I believe is a masterful piece of research, which is the uniform convergence of empirical means. So what they did is they took a class of sets and they wanted to simultaneously estimate the probability of these sets based on the empirical value, empirical mean. And they showed that convergence of the empirical mean towards the true probability takes place whenever the class of sets has a finite DC dimension, finite Vapnik-Chervonenkis dimension. Later, this result turned out to be fundamental for learning schemes because, I mean, pretty much what happens is that if you can learn the probability from empirical measures, all of them simultaneously, then you get a big picture and hence you can judge. Now, it happens that in many contexts, we do use algorithms like this one, for example. This is a optimization with a relaxation, or more general, we do decision making based on data, and we come up with a solution. So it is also true that we are not so much interested in uniform convergence in this context. So when I'm given a solution, I'm interested more in the risk associated with that solution. And it may happen very well that in this context, the VC dimension is infinite. So refer back to my initial example, the one of the convex hull. If you consider the set of all convex sets on R2, this has infinite VC dimension, and hence uniform convergence does not take place there. Now, in this context, in this general context, it remains true that the risk tends to risk hat, where risk hat is this ratio, where the numerator has the empirical violation, Ci bigger than 0, where in that context points are outside. But this must be complemented with this other portion. And this ratio is something such that the real risk tends to risk hat. And this holds true even in case in which the VC dimension is infinite. So referring back to the case where we construct a convex hull, in that case, this part is 0, because just keep in mind that all the points are inside. Still, it is not true in general that this ratio goes to 0. And this is why this convergence takes place. So I know that much more might be said about this, but I just wanted, time flies, so I just wanted to sow the seed here for future investigation by others if they are interested. So the same thing as before apply. So for example, in the two-sided case, we do have that the risk has to lie within these two limits. And of course, we can also find the cost when rho varies over a grid. And so you may experience this, and the corresponding, the risk based on the theory. And by the way, this graph refers to an application example that I would like to show you next. So these are 2000 data points. This example is taken from an old paper by Peter Bartlett, Alex Mola, Sholkoff, and Williamson. And what we did is that we constructed a region based on support vector regression as given here. In this context, we used a Gaussian kernel. So there is a feature map, and importantly, we used 15 different values for rho, for the parameter rho. And we found out this situation. So this value is computed. This you optimize and you find the value, whereas this region is given by the theory. And based on this, you can make your selection, cost versus risk. So we selected this value, where the risk dropped to 0.3, with a big drop from the initial value, while the risk is kept low. In this example, which is two-dimensional, so very easy to visualize, I can also show you the solution, which is this one. Let me just mention that if you go to the two extremes, in the first case, the risk is very low, but the value is large, and vice versa here. And again, this is a toy example where I can visualize. So the first case is a very large region with a lot of empty space. In this case, then you are pushing your luck too much. Okay, so possibly this brings me to my conclusions. So what I tried to convey to you today is there's a story that complexity and risk have tight links at a very fundamental level. Let me tell you that developing this theory took a long time. I've been working on this topic for 15 years or so. This is a message for the young generation. I know that people these days are having a lot of pressure for generating results, publishing results, and so on and so forth. But my advice to you is to save some time for deep research, because at the end of the day, this is the only research that provides you with a true and deep fulfillment. I believe that it's a beautiful math, and it brings useful results to the world of applications. And what I really value above all is that it tries to unveil some key mechanisms by which knowledge can be created out of experience. And I'm not talking here just of my own research. I'm talking of all research being done by many people in machine learning working on fundamental facts. Because I do believe that the most important problem in science is to create knowledge out of experience. All we know about the real world comes from experience. And what are the mechanisms by which we can draw knowledge and we can foresee new out of sample cases based on that? And unveiling this key mechanism, I believe, is the most important problem in science. And finally, this is also an extra message for the young generation. I believe that we have barely read the first page of this story. So there are incredible opportunities of research. Thank you all.
Okay, thank